This gives us now both a formula for constructing the representation or doing the synthesis, as well as for finding the weights of the representation, which is called doing the analysis. So, synthesis as we said x t is given by this kind of a sum k equals minus infinity to infinity x k e to the j 2 pi k t by t. It is a sum of exponential functions. Each exponential function is periodic and harmonically related to the x t in question. Then we have the analysis equation. X k is given by 1 by t integral 0 to t x t e to the minus j. The minus is there because we complex conjugate the second member of the correlation, 2 pi k t by t dt. Okay. So, now we have defined the Fourier series. With these two equations, the definition of the Fourier series is complete. But as I said, there are still a lot of questions to answer, lots of things to explore. For example, we would like to know what sorts of signals this thing is definitely this approach is going to work. For what sorts of signals this approach will work. Let us take a look at certain obvious properties. Now, one of the facts, common sense facts is that when you add continuous functions of time, the result is always a continuous function of time. So, if this is true, then since each component in the synthesis is a continuous function, because complex exponentials, periodic complex exponentials are eminently continuous functions, extremely continuous functions, they do not show discontinuities anywhere at all, then their sum must also be a continuous function, and hence it is not possible at this level of analysis, at this level of reasoning, to ever believe that x t such as a square wave can be represented using the Fourier series, because if we could do that, then clearly we are constructing a non-continuous function, a discontinuous function using continuous components. That is just not possible. But there is something else to look at, something that should sober us down, and that is the fact that while the sum of a finite number of continuous functions is continuous, here we are constructing a sum of an infinite number of continuous functions, and maybe something funny is happening over there that allows us to make a discontinuous function by adding up continuous functions, if you just add large numbers of them in sufficient numbers. Now, this is not a discussion that would be very convenient to do at this level in any kind of detail, because it goes into all kinds of intricacies in the mathematics of Fourier analysis, which is really not expected in a course at this level. So, all I will do is to say that continuous functions, if x t is a continuous function, then there is absolutely no problem in representing it using the Fourier series. You can even say several more things about it. For example, you can say that if x t is continuous, then for every t in the interval 0 to t, the partial representation, that is the truncated representation of the Fourier series, will come closer and closer to x t. Let us put this down. For xt a continuous function, for all t in 0 t, that is in one period, it is the case that limit as k tends to infinity of k equal to minus capital K to plus capital K. This is also limit as capital K tends to infinity, x k e to the j 2 pi k t by k equals x t. That means, for every point of time over which x t is periodic, that is from 0 to t, this representation will converge to x t. So, this is the simplest and the best case. Now, there are other things that can be said about the existence of the x case. So, this is point number 1. Point number 2, existence of the x case. By the way, for the case 1, when x t is a continuous function, we will also say, before we start on point number 2, that will exist. Second, we have in fact we take up the discussion of when these x k's will exist. What is the necessary condition to be satisfied for the x case to exist? The necessary condition is the following. When integral 0 to t x t when this is finite, that is when x t has finite power, then we can say the following. This representation minus the original x t will have no energy. Also, all x k's will exist. Now, there are two different things being said over here. First, that the coefficients of the representation will exist when x t has finite power. The second thing is, when x t has finite power, then the difference between x t and its representation will have 0 energy. Now, that is a very ominous thing. That is almost like saying, in fact it is saying that this representation need not necessarily be equal to x t at all points t in the interval 0 to t. This means that the representation and the original signal possibly differ at some points. This is nothing to get alarmed about. Now, remember that for the case 2 that we are presently discussing, we have not imposed upon x t the constraint that it should be continuous. That was case 1. When x t was continuous, you had all the nice things in life. For case 2, we are considering any x t which has finite power without imposing any further constraint on x t itself. For example, x t could be a square wave, which is certainly not a continuous signal, but it still can have finite power. In fact, a normal square wave has finite power, and therefore, it is amenable to a Fourier series representation. However, it is said that the representation will not match the signal probably at all points, but its power will be 0. In short, we will say that if we evaluate, not there is no need to write if over here, we are just saying that x hat t minus x t, this whole thing squared dt integrated from 0 to t will be 0. Now, it is an important fact of engineering life that when two signals do not differ in energy or do not differ in power, then for all engineering purposes they may be treated, they may indeed be treated as identical. If they differ in power, then alone will an engineering system be able to distinguish the signal from the representation. If they do not differ in energy, then the error has 0 energy, and therefore, the two signals, the original and the representation, cannot really be distinguished. That is, from an engineering point of view, viewpoint, x hat t is practically as good as x t itself. So, while the purist or the mathematician will still find this very exciting, we say, well, that is good enough for us. If they do not differ in energy, then that is fine enough for us. A more precise treatment of, I mean, you see, this second statement that we have made is not telling us exactly, it is only telling us that the representation and x t will not be identical to each other. It does not tell us at which points it will not be identical, at which point will it indeed be identical. It is not telling us any of this information. However, as we said, it really does not matter to us. As engineers, we do not have to be worried beyond this point. However, point 3, which discusses the Dirichlet's conditions, is a very nice treatment that gives us more precise requirements to meet a certain kind of resemblance. Dirichlet's convergence conditions. Now, Dirichlet's convergence conditions essentially impose 3 requirements on x t. The first requirement is absolute integrability. That means, the integral of the absolute value of x t over one period must be finite, right. Now, the second constraint is bounded variation. That is to say that x t is allowed to have at most a finite number of alternations maxima and minima. In other words, over one period. Third, x t is allowed to have at most finitely many discontinuities of finite height. X t is allowed to have no discontinuities of infinite height. Which is a constraint, but nevertheless a happy constraint, because the positive way of looking at this constraint is to say that means you are allowed to have discontinuities of finite height. However, is allowed no discontinuities of infinite height, and at most a finite number of finite height discontinuities finite number of finite height discontinuities over one period. All right. So, 3 conditions in all. So, what do we get for obeying all these 3 conditions? After all, if you obey the rules, you must get something for it. This is what we get. For any x t, that meets the 3 Dirichlet conditions, convergence is assured at all points where x t is continuous. At all points t, at all t where x t is continuous. At points of finite discontinuity, at points of finite discontinuity, x hat t is given by x hat t equals x of t minus epsilon plus x of t plus epsilon divided by 2. So, it just takes the midpoint. X hat t takes the midpoint. Value, midpoint value at the discontinuity. So, the Dirichlet conditions are probably the most transparent and frank discussion of the convergence properties of the Fourier series. If we look at convergence issues in terms of the Dirichlet conditions, we not only get to know whether it will converge, we also get to know where it will converge and where it will not converge, and also beyond all this, how much or what value x hat t will have at those places where it does not converge. There is almost nothing else left to be said, except of course, if you are curious enough to ask what happens if it does not satisfy all the 3 Dirichlet conditions. Now, suppose you do ask that question, then the answer is very, very long. It goes on and on for different cases of different kinds of complications. All we can say is that the guarantees A and B given in this page regarding Dirichlet's conditions will not be met. So, it is difficult to discuss such signals. All right. Now, so much about the properties of the existence and convergence of the Fourier series. Now, we will go on to one more thing. Question B, the only thing that was left. or rather I do not know if it was question C. Let me just go back a couple of pages and take a look. Yeah. Now, the question of what we can say about the truncated representation as we go on adding more and more terms to the truncated representation to bring it to the complete representation. What can we say in short of the value of what I will call x hat k, capital K of t, given by the sum small k equal to minus capital K to plus capital K of x k e to the j 2 pi k t by t. Now, what I want to therefore ask is, I want to discuss how x capital K hat of t, which is the kth approximation, you can say. The first approximation is the coarsest, second is a little finer, and so on, the kth approximation. Discuss how x k of t resembles x t. Okay. In order to discuss this, there are some very straightforward nice properties that the Fourier series has. The most nice property is that signals taken from different periodic from different preserved classes absolutely do not correlate with one another. In short, they are what you call in linear algebra as orthogonal. That means, if you take integral e to the j 2 pi k t by t and correlate it with e to the j 2 pi l t by t, that is e to the minus j 2 pi l t by t. Remember, I am putting a minus sign here because the second member of an inner product has to be conjugated, dt from minus infinity or sorry, this is from 0 to t, 0 to t. What can we say about this? As I said, this is something we have already discussed, it is a pretty obvious fact. It is simply that this evaluates to 0 when k is not equal to L, equals 0 for k not equal to L, equals t when k equals L. We have this fact. Now, what this can be shown to lead to is the following fact, that if x t has a certain representation in terms of a Fourier series, then this representation as seen from the truncated series x hat k of t gets closer and closer in energy terms, or rather in power terms, if you like, energy per period terms, to x t as we add more and more coefficients, as we add more and more terms in the truncated representation. Furthermore, the choice of coefficients x k, small x k over here is not determined, the choice of best coefficients is not determined by the choice of the truncation limit. Let us put both these statements down properly. Now, suppose we are concerned with a truncated representation. Let us say with a truncated 2 k points representation. Then one does need to ask the question, since now we have a truncated representation as shown over here, one does need to ask the question, are the xk's that act as weights for combining the exponentials the same values as you would use for the complete representation? In short, the choice of the coefficients, the weights of the combination, will they change if you have a truncated representation instead of a complete representation? Okay. Now, the answer to this is very nice. The answer is no. In short, if you only wish to minimize the energy, that is to say, if you calculate, you wish to choose xk minus capital K less than small k less than capital K, if you wish to choose xk with the view to minimize integral 0 to t xt mod xt minus x hat k of t squared dt. That is to say, if you wish to minimize the energy of the error and choose such xk's as would minimize the energy of the error, then irrespective of k, of both capital K and small k, xk is the same, evaluates to the same number as for the untruncated representation. The coefficients do not have to be recalculated. Thus, out of say practical considerations, if you wish to represent an xt with say the first 100 Fourier coefficients, maybe you do not have enough money to compute more coefficients, but later on tomorrow you are richer and you want to have a more accurate representation for xt, then you do not have to go back and recalculate the old xk's. They will continue to hold, they are still the best xk's you will have. You can now calculate another 100 coefficient terms and have a 200 term representation for xt. The new 100 coefficients will certainly have to be obtained, but the existing 100 coefficients which you used to construct the 100 point truncated representation will not be affected by the extension of the representation to 200 coefficients. That is the crux of the fact that this is an orthogonal representation. It is an orthogonal representation. That, as I said, it simply means that if you take two of the representing functions from two separate preserved classes, then their inner product over one period evaluates to 0. If they are only from the same preserved class, you will get a non-zero coefficient of correlation. So, their coefficient of correlation is 0 when they come from different preserved classes. So, it is because we have an orthogonal representation that the choice of coefficients that you will use for a truncated representation is the same that you will use for the untruncated representation. Okay. So, that is an important milestone in our study of the Fourier series. Now, let us see whether we can say something more about the Fourier series, how to take it further. For example, as to solving examples to obtain the Fourier series representations of various functions, we are not going to do that here. There are enough textbooks. This video course is meant to support information that you can already get from books. So, we are not going to spend time solving simple examples over here. Okay. Now, an important property of the Fourier series coefficients is that they are generally complex. They are generally complex numbers, and because they are complex numbers, we will have to see how, when these complex weights are used to generate a combination of the preserved functions, the basis functions, how it is possible to construct a real function of time x t. Suppose x t is real. Suppose x t is real. That means, the Fourier series evaluated over all the values of k should add up to a real number equal to the value of x t for all t between 0 and capital T, that is for all t's over one period. The Fourier series should not make silly mistakes like going wrong and giving you complex values for a function which is itself inherently real. Now, how does this really happen? It happens by the fact that the coefficients x k for negative k and the coefficients x k for positive k are complex conjugates of each other when x t is real. The coefficients x k and x of minus k will be complex conjugates. Okay. Thus, for example, if you have x 3 equal to 2 minus j 4, then x minus 3 will be equal to 2 plus j 4. It is because of this pattern followed by the coefficients that the complex valued functions, basis functions, add up so as to cancel their imaginary parts and leave behind a purely real function x t, because we started with a real function. Now, suppose we started with a purely imaginary function, then what happens? Suppose x t is purely imaginary. Then pairs of coefficients x k and x minus k would be conjugates and have a minus sign. X k equals minus x star of minus k. This is the only way you can make sure that the real parts cancel, leaving behind only the imaginary parts. Of course, this ensures, the second part ensures that x t is purely imaginary. The earlier case we discussed ensures that x t is purely real. So, that is how this is ensured. Now, there is a nice name we have for this relationship between the corresponding pairs of Fourier series coefficients for k positive and k negative. When x k equals x star of minus k, which is the case for x t real, we say that they are conjugate symmetric. And that is when you have x t real. On the other hand, when x k equals minus x star of minus k, we say that they are conjugate antisymmetric. And x t, this corresponds to the case of x t imaginary. Fine. Since we have an array of discrete coefficients indexed for different values of k, k running from minus infinity to infinity, it becomes worth looking at making a plot of these x k's for different values of k. If we made a plot like that, it would ideally have 0 in the middle, and for different values of k you will have k equal to 1, 2, 3, 4 on this side, minus 1, minus 2, minus 3, minus 4 on this side. Now, what can we plot on this? We really cannot plot x k itself, because x k is a complex number and you can't just put down only the real part or only the imaginary part of a complex number. We really have to make two plots. Therefore, this you can say is real x k and then you can say its value here is this much, its value here is this much, its value here is this much. It can be both positive and negative. Its value here is so much. Here you can say its value here is this much, this much, this much, this much, whatever we have made. Similarly, you will have a different simultaneous plot for the imaginary part. Here again you will say it's this much over here, this much over here, this much over here, this much over here for 1, 2, 3, 4, and maybe for minus 1, minus 2, minus minus 3, minus 4, you can have some values again, maybe this, whatever. So, you need two plots to completely describe these, and these are essentially discrete plots. The sort of plots you would make for a discrete time signal, you are making them for the Fourier series representation. It is a discrete sequence indexed by k, k going from minus infinity to infinity. Alternately, you can have what is called a polar plot. Well, it is not really a polar plot so much as a plot where you express the x k's not in terms of the real and imaginary parts, but instead in terms of their magnitude and phase. So, you would have one plot where you plot mod x k and another plot where you would have angle x k. Fine, this is what you would have. Now, you see an essential feature here is this. This also is discrete. Mod the magnitude plot is also discrete, the phase plot is also discrete, because it is available for only discrete values of k. So, you will get some plots which look like the real and imaginary plots we have made, but then certain patterns can be discovered. When x t is real, conjugate symmetry holds, and in such a situation you will find that mod x k is even. Let us list all these properties over here. Let us say x t real, and here we will say imaginary. Then real x k, so this is for x t real or x t imaginary. Real x k will be even, imaginary x k will be odd. That means to say x k will be equal to x of minus k, real x k will be equal to real x of minus k, and let us list all these properties over here. Okay. X t can be purely real, purely imaginary, or neither, that is generally complex. So, let us say x t is real, imaginary, or complex. Fine. Now, when x t is this, we will look at the symmetry properties of the real parts of x k, the imaginary parts of x k, the magnitude parts of x k, and the phase parts of x k. So, let us consider real x k. The real part of x k will be even when x t is real. The imaginary part of x k will be odd when x t is real. The magnitude part of x k will be even when x t is real, and the phase part of x k will be odd when x t is real. This is the set of properties you can expect when x t is real. When x t is imaginary, precisely the opposite happens. For example, the real part will be odd, the imaginary part will be even, the imaginary part will be even. As to the magnitude and phase, I will let you find out by yourselves what it is going to be. Please remember that the magnitude function can never be odd, because odd functions have to be negative in some places at least, and magnitude functions are never odd. So, try to figure out what you will have to write here and what you will have to write over here. What will be the magnitude and what will be the phase? What properties they will have? What symmetry properties they will have? Now, coming to the third column, where x t is complex, this is the most general case, and so generally symmetry properties, no symmetry properties may be expected. All we can say is that dash 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 dash. You can't say anything about the symmetry properties for the general complex case. Now, if for a real valued x t, which is what we often like to deal with in real life, we were to make a magnitude plot, it would look like this. Symmetrical, as you can see, conjugate symmetric or simply even. Now, the phase on the other hand would be like this. this is how the phase would be. So, this is just an example for x t real. Okay. So, now we know how to make magnitude and phase plots. Now, let us just start looking at what happens to the Fourier spectrum if time undergoes certain changes. For example, let us first try to relate what these positions are along the time axis, along the k axis. What do these k's really stand for? The k's, the different values of k's stand for different so called frequencies. A Fourier series analysis attempts to express the signal in terms of different components that are often given a physical connotation. Of frequency. That means to say that we say that these different Fourier series coefficients correspond to the contribution of different physical frequencies to the signal x t. Now, there can be a lot of debate about taking this meaning of frequency, but let us not enter into that debate, because it is very widely held that they have certain physical meanings. They do indeed have physical meanings, but this notion of relating frequency or rate of change to different Fourier series coefficients is problematic at a certain level. I will merely say this and leave the debate at that. Now, let us instead look at what happens to these different frequency coefficients. We see that essentially in the frequencies or in the parameters of the exponentials that are used in the representation, we can indeed give a connotation of frequency to the parameter. When you have e to the j 2 pi k t as a certain periodic complex exponential, we can denote 2 pi by t by some frequency omega naught. If we give this notation of frequency, if we write this as omega naught, then omega naught will be called the fundamental frequency. Clearly, the larger the period of x t, the smaller the fundamental frequency, because it is 2 pi by t, where t is the period of x t. So, if t is large, omega naught gets small. This allows us to compare the spectra of two signals with different periods, and I am just going to make some sample spectra of two signals with different periods so that we can look at them. I will just make the magnitude plot, not the real or the imaginary or the phase plot, just the magnitude plot to show what happens. The second thing is what this k is doing over here. K represents multiples of the fundamental frequency. So, you have constant multiples, increasing integral multiples of the fundamental frequency that contribute to the Fourier spectrum of any x t, periodic x t. So, let us make, let us say t 1 equals 2 t 2, and we are concerned with x 1 of t equal to x 1 of t minus t 1, x 2 of t equal to x 2 of t minus t 2. Suppose we have t 1 and t 2 given in this format. Then let us try to understand what the Fourier spectra are likely to look like. Suppose I plot mod x 1 k. Remember that t 1 equals 2 times t 2. That means omega naught 1, which is the fundamental frequency for x 1 of t, will be half of the fundamental frequency of x 2 of t. So, here you have k, or we can write this as k omega naught and write this as 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and so on. So, then you will find that you have pillars in each of these places. I am trying to represent a real valued signal. So, it will be conjugate symmetric. No negative values because it is the magnitude plot, magnitude is never negative. Fine. Now, mod x 2 k. Here we had k omega naught 1, now we have k omega naught 2, but omega naught 2 equals 2 times omega naught 1 because t 1 equals 2 t 2. Keeping this in mind, these points at which we make the Fourier spectrum plot must be chosen twice farther apart from each other than was the case for x 1. So, you will have 1 over here, 2 over here, 3 over here, far apart from each other, minus 1, minus 2, minus 3. Then you would have some plots like this. The fundamental difference between this plot and the previous plot is that the magnitude spectrum of x 2 t, x 2 k looks extremely sparse compared to that of x 1 k. Now, this is the important significant point about the effect of the choice of the period, effect of the period of the periodic signal upon its Fourier spectrum. From now on, we will not plot Fourier spectra for Fourier series using k as the index, but using k omega naught as the index, because the moment we do this, we have a handle on the actual physical frequencies that are involved. We would not have that if we just dealt with k and suppressed omega naught.